So last time we basically discussed two resolutions of this infrared problem in QED. So one of them had to do with basically evaluating these inclusive cross sections. So roughly speaking, we saw that diagrams of this kind, where you sum over ladder exchanges of photons, and then compute the associated cross-section together with diagrams of the same sort, but that involve arbitrary emissions of soft photons. So we drew these like this last time. To infinity, that these were IR finite. And so the idea here of including these soft emissions was to was basically the fact that detectors are not sensitive below certain energy. And so if you want to compute an observable, you don't only, like, basically an electron is indistinguishable from itself plus an arbitrary cloud of, say, n photons with energies below the detector sensitivity. So, and roughly speaking, the infrared divergences that came from these ladder exchanges cancel with the exponentiated infrared divergences arising from the soft theorem, basically. So this was one resolution, sort of, and then we also talked about the second one, which was that alternatively, so we discussed this idea that we still, if we do this, we still have ill-defined S matrix. And so, however, one can also try to resolve this puzzle at the level of the S matrix by basically computing the S matrix in the basis of so-called dressed states. So we had something like this. So collection of outgoing momenta. And we said that this is also IR finite. And roughly speaking, here, these addressed states, we discussed them last time. We sort of introduced them based on the fact that electrons by themselves are not gauge invariants, but an electron together with its Wilson line that extends all the way to infinity is. So you can think about this as so this is hard particle so like an electron or a positron, and this is like the Wilson line. And we also mentioned this Fadeev-Coolidge dressings. Okay, so last time we sort of concluded by saying that all of this also has to do with asymptotic symmetries or large gauge symmetries, and we promised that we're gonna revisit these questions from this point of view. So this is the subject of today. So so let me introduce them in hopefully what's going to be like quite a straightforward way. I mean, there are a lot of subtleties in the subject, and there's many ways to think about this problem. So let me start off by talking about free E&M. So we just have a Maxwell action that is basically f mu nu up to some factor. And we know that if we vary the action, in that case, we get the equations of motion, which are just d star f is equal to 0. Right, so this is just d mu f mu nu is equal to 0. And if you take the pullback of this equation to a Cauchy slice in space-time, we get what's called constraint. So this leads to, so evaluated on a Cauchy slice sigma, so-called Maxwell constraint. And so we know that upon quantization, so then you can think about these this field strength as consisting of both Coulombic and radiative modes. And in the quantum theory, what one usually does is take this constraint and imposes, quantizes the field and then imposes this equation as a physical state condition on physical states. So all physical states should obey this equation. So in particular, if we take, as I said, we need to take this and evaluate it on some Cauchy slice. But of course, I can also, I have the freedom of multiplying this by some arbitrary function of x, and where x is a space-time point. And this equation should still give me 0, right? Because this is just trivially by the fact that d star f is equal to 0 anywhere in space-time. So, and for now, let's just take this function psi to have compact support. So now my claim is going to be that in this case, one can also think about this object as a generating gauge transformations. So this condition is nothing, says nothing but the fact that physical states have to be invariant under sort of small gauge transformations. So let's see how that works. So to see this, we just take this equation and basically integrate by parts. So if we take this integral of this function psi against d star f, I can use Stokes' theorem to write this as the integral over the boundary of sigma of psi. Okay, I'm using, just realized I'm using zeta. Anyways, so zeta star f, and then minus integral over sigma of d zeta wedge star f. Yeah, and we want this to vanish when we impose it on physical state. But because we are considering, for now, transformations or sort of functions, zeta that have compact support, this thing vanishes on the boundary of sigma, right? Because you can think about like, like a Cauchy slice, like a three-dimensional slice in 3 + 1 dimensional space-time, and this would be something like a sphere at infinity or something like that. So obviously this is 0 by assumption. So by this assumption, and so we are just left with this formula. And but now the claim is that this is just, when we write it in this way, this is just the generator of gauge transformations, parametrized by zeta. So if it's not clear, let me remind you how that works. So even already in the classical theory, one can compute the phase space associated to Maxwell theory, and this phase space is equipped with a symplectic form. We're going to see more on this later when we discuss gravity in more detail. In Maxwell theory, it's very easy to find the symplectic form, and it just pairs the gauge potential A with basically the field strength. And so to see this, we compute the Poisson bracket of this object with A, right? And if this is indeed a generator of gauge transformations, this thing should give us something like d zeta, right? So if these were actual global symmetries, these would be generating symmetry transformations. Here, these are just constraints, so they should be generating redundancy. So they should be generating gauge transformations on A. And actually, this follows from the fact that the symplectic form in E&M is basically proportional to integral over d star s wedge dA. So, okay, there's going to be more on this later. This was just the exterior derivative on phase space. And this is a wedge that is both a space-time and a phase space wedge. So this object is a true form on field space, and it is, from a space-time point of view, it's just the evaluation of basically star f wedge A on some Cauchy slice. So this basically tells me that star f and A are canonically paired, just like momenta and position are in quantum mechanics. And so here from the bracket, I can just, there is some algebra that one can do. For example, you can do it in coordinates by choosing your favorite Cauchy slice and using the canonical brackets of star f and A evaluated on that slice and computing this this Poisson bracket to find this nice relation. Yeah.
I don't understand why the star equation doesn't put down constraints. Why we consider something of that cool? Like why we put this side that makes symbols cool in the first place? Like why we put that
Well, because I know that this equation is true by Maxwell's equations.
Okay, but why do we have to consider this side or this side?
I'm just saying that this is a true, I mean, I'm starting with just a true statement. If d star f is equal to 0 anywhere in space-time by Maxwell's equations, this equation is also going to be true. Well, because I want to connect it to these charges, and later on we're going to see that this thing does not necessarily, I mean, what? Yeah, let's just maybe like, let me just proceed, and then we can return to this question in a bit. It's basically like, I'm writing it this way to basically show that this constraint is also the what I have shown is that, or rather argued, I haven't done all the steps, but this constraint is actually also a generator of gauge transformations. And it makes sense. Like, basically what I'm saying is that physical states should be invariant under gauge transformations. And this condition can be also thought of saying that, you know, like physical states, if you think about them as being built by acting, for example, with like quantized modes of the, say, gauge field, then you have to like dress those in an appropriate way such that you end up with something that obeys the constraint or equivalently is invariant under gauge transformation. So
just some simplification. So normally it's a bad idea to define that quantum bracket in gauge theory, right? Exactly because redundant is yeah, you know, the generate and they define the theorem bracket and blah blah blah.
yeah.
So this omega the generate is already like.
So actually, no. If you choose your slice accordingly, you are going to find basically that it's only the radiative modes of A that are the things that are usually physical that you actually end up quantizing.
Right, but there is no physical problem. It's only that physical, right? So that's.
Yeah, but I mean, you can still, I mean, when we compute, for example, scattering amplitudes in ENM, we still talk about photons in the asymptotic state. So naively, those are also those are just constructed. Photons are just like modes of the radiative field. So
yeah, sure. But then you have if you want to do organizations.
Yeah. No, exactly. I'm gonna go there. I'm just saying that at this point, this is what this is what you'd be finding if you go through the analysis of the constructing this. Okay, actually, maybe I should have done this because it's actually I'm saying it as if it's like a complicated thing. You just write down the Maxwell action, and then I'm going to describe actually next time like how to work out the canonical, like I'm going to do a covariant phase space formalism, and I'm going to describe how to construct the symplectic form. In ENM is actually very easy. You just have to do some integration by parts. So let me, for now, let's just take this as a given, like basically that star F and A are canonically paired variables in ENM, and that this then implies, so once you believe this, then this automatically implies that this object generates gauge transformations. And that condition that I'm writing there is just a statement that physical states should be invariant under gauge transformations. So that's the only message I want to convey at this point. And we're going to do this in more detail next time. So if this, I wouldn't worry if this is not very familiar. Yeah.
No, I thought that was another zeta. It's open bracket. Yeah, it's an open bracket. I thought it was a zeta. Now the first one. The first one looks like a zeta.
This?
Yes.
No, this is just, sorry.
Sorry.
No, it's just this is just a Poisson bracket, yes. So, yeah. So this tells us that this thing generates gauge transformations and this star condition just tells us that physical states have to be invariant under gauge transformations with compact support. So actually, this is just, it was supposed to be like sort of a review of like what we do in ENM. So yeah, so the important fact was that we usually, if you go back to your assumptions, like it's always assumed that your gauge transformations have compact support. So however, I mean, there was no reason to consider such gauge transformations in the discussion that we had so far. So So now let's generalize this. So this equation here will still hold in free Maxwell theory, right? Even if a zeta doesn't have compact support, it's just integrating d star f, which always has to be equal to 0, yeah? Just by Maxwell constraints. So this holds also when this when this zeta doesn't go to 0 at infinity. So in that case, I can still redo this analysis here, but so we still have 0 is equal to integral of sigma zeta x d star f. But now when I integrate by parts, I'm not allowed to throw away this term anymore. So this is now just going to be so I'm just copying what we had before.
Is the top, is something to say when it doesn't go to 0? You know, it says it holds when zeta goes to 0.
This always holds. This is just d star f is equal to 0.
But wouldn't the boundary term also vanish going to 0?
I think at the top there, when the set goes to 0, it's no.
Oh, sorry. Oh, sorry. Yes, thank you. Sorry about that. Yeah. Yeah, so the key thing is that this term doesn't vanish anymore now. And so however, the second term, this thing is still my generator of gauge transformations by the same argument that we had before. So this is just saying now that the generator of gauge transformations doesn't coincide with my constraint anymore. And this is because of the presence of this boundary term. So this is still the generator of gauge transformations. However, what we see is that the constraint now is not the same as the generator of gauge transformations. And in particular, the two differ by the term in the first line here. So the integral over d sigma of zeta x star f. So so I'm going to call this q sigma, because on the one hand, by the constraint, this thing generates gauge transformations. Okay. So from this equation here, I find that q sigma acting on A is still d sigma. But also, q sigma is not required to vanish, right? Unlike before. So, in other words, q sigma becomes a physical charge. Another way to say it is that while previously the generator of gauge transformations obeys so-called first-class constraints in the presence of boundary term, the first-class constraints in classical mechanics are promoted to second class, and there is an obstruction to basically imposing that these q sigmas vanish in the presence of boundary terms. Sorry, algebra of constraints is promoted in the presence of this boundary term.
It's supposed to be the boundary term.
Yeah, I'm just. No, so here I'm just saying, so I'm always taking as my fundamental equation, again, in the thing in the first line. Yeah. And I'm just saying that now, when I have a non-vanishing d sigma, like such a boundary term, this is going to be equal to minus that, which is the thing we computed before, by the fact that the linear combination of the two is equal to 0. And hence, this means that q sigma still generates gauge transformations because you can still do the exact same analysis before. It's not going to be affected by this. However, now q sigma is not equal to 0. It's actually equal to this boundary term. It's just that. And so you cannot, actually you can check by computing this algebra of these q sigmas that you cannot consistently demand that this thing vanishes when imposed on physical states. So, okay, so this hopefully was not very confusing. Should be. I mean, this is the key idea. The key distinction between small and large gauge transformations. So large gauge transformations basically are generated by, so are associated with parameters that don't have compact support, so they are non-trivially supported at infinity, and this gives rise to these additional boundary terms that one finds in these constraints, and that these cannot be consistently imposed to vanish. So generators of gauge. So now these gauge transformations become actual symmetries. So you are allowed, when these are symmetries, asymptotically, your physical states are still allowed to transform under them. So, and now what we're going to see is, so now we're going to try to see what the implications are of basically the presence of such charges in for example, in ENM, on scattering, so as before. And we're going to see that depending on the basis of states in which we calculate, so we're going to see that basically these charges will lead to conservation laws, as they usually, as you know, usual charges associated with global symmetries do at the level of the S matrix. And then those conservation laws, depending on what basis of states we evaluate them in, will either lead to soft theorems or to basically the stressed amplitudes that we discussed before. So for example, so that just to give a preview, so this Q zeta will demand that they are conserved. We will also not necessarily demand, we will also explain this requirement. In scattering processes. And just to connect with what we said last time, so sort of this is going to be the point B, the second point that we will discuss, but one implication will be that if we scatter eigenstates of these Q sigma, then we find that this Q sigma has to be conserved in time. The conservation law tells us that the initial net eigenstate of the state that we are scattering has to be equal to the final eigenstate. So if we scatter eigenstates of sigma, so we have a picture like this. Again, time goes this way. So we have Q sigma acting on some initial state has to be equal to Q initial psi initial by assumption. And then the final state, we have Q zeta psi final, Q is equal to Q final, psi final. Right, so we start with an eigenstate of Q sigma, with an eigenstate of Q zeta, and we end up with another eigenstate of Q zeta. Conservation then implies, like in quantum mechanics, that the eigenvalues have to be the same. So Q initial is equal to Q final. So if that happens, then Q initial has to be equal to Q final. And essentially, this kind of setup where we scatter eigenstates of large gauge charge turns out to be equivalent to the Fadeev-Kulish or Drest state prescription that computes I at finite amplitudes. We'll also look at implications of this conservation law when we don't scatter eigenstates of large gauge charge, and then we will see that the implications in that case will just be the usual soft photon theorem. So yeah, I think questions about this?
Remove the large gauge transformation like normal symmetry in the system.
Yeah, pretty much. Yeah, and in ADS-CFT, for example, we also know that large gauge transformations in the ball, or we don't know. Okay, so it's a bit, yeah, so large gauge transformations are a bit more similar to usual symmetries, but they are still associated to diffeomorphisms or gauge transformations that don't have compact support. So they extend all the way to infinity, and then, yeah, in some holographic theories, these usually end up corresponding to actual true global symmetries in your boundary sort of CFT. Yeah. Yes, exactly. So we'll discuss this actually later today. So, I mean, the way we are going towards gravity still. We're going to discuss gravity at the end of, like, sort of in the second half of the second lecture today, and next time we'll complete that story. But basically, like, I'm trying to give a complete story in sort of QED that also includes these large gauge charges, because the gravitational case is just basically going to be, the philosophy is going to be essentially the same. It's just technically maybe a bit more involved, but yeah. Okay, so yeah, so what do we want to do? So we want to analyze a bit closer what we mean by conservation. So what does this thing mean? So what does it mean that I require these large gauge charges, Q zeta, to be conserved in any scattering process? So since we are talking, so we're talking about QED. So previously, when I illustrated this, I only talked about free Maxwell theory, but I can include actually current in the game. And so now let's consider E&M with charges or currents. And actually, the definition of this large gauge charge in that case is still going to be this. So we still have this Q zeta be the large gauge charges, so zeta function of x star f. So why do I call this large gauge charge? Well, again, by the same logic here. We want this thing to generate now gauge transformations on both the gauge field and on potential matter fields that are present. So these charged particles that we allow here to have, that we are allowed to have. So to see this, we basically do the same thing as before. Now the Maxwell constraint is modified a little bit. So we have, we have 0 is equal to integral over sigma of zeta x. But now my Maxwell constraint is d star f minus star j, okay, is equal to 0, right? So this is still my true equation. And now I can integrate by parts. So the first term is essentially what we had before. So this gives two terms, d sigma integral over the boundary of sigma of this zeta x star f minus integral over sigma of d zeta wedge star f. And then we have the second term. So minus integral over sigma of zeta x star j. And yeah, and basically this is still the generator of gauge transformations on A. And this will turn out, once you like write the current J is usually expressed in terms of your matter field, in terms of the charged particles, and it turns out that this generates gauge transformations, infinitesimal gauge transformations on those matter fields. So one generates, so still generates two generates so these are large gauge transformations. So the combined, and just as before, now what we have is that the combined action of the generators of large gauge transformations on photons and matter fields has to be given by the same object that we had before, so this Q zeta. So to understand the effect of these charges on scattering amplitudes, let me first draw. So we have to be a little bit careful. We have to be careful about where the asymptotic states are defined in the Maxwell theory. So Um, So if we have Minkowski space, you may recall that we can draw it on a Penrose diagram, so on a conformal, in a conformal compactification. So basically, this diagram preserves the space-time structure, but it also allows you to like visualize what's happening at infinity. And so there are a few distinguished places in this diagram. So there are time-like infinities, I minus past time-like infinity, and I plus future time-like infinity. And then we have null infinity, so again, past null infinity or scri minus, and future null infinity scri plus. And then we also have space like infinity I0. And you can think about, so in this conformal compactification, Minkowski space near infinity looks like two null cones, like the union basically of two null cones. And in particular, massless, if you just look at massless particles, you will have them come in from past null infinity and reflect sort of, and then, sorry, I should also tell you like what this is. So we have on these diagrams, you can compute sort of the surfaces of constant radius r. So for example, you can take Minkowski space in retarded coordinates. U is t minus r is a radial coordinate, and then you can have two angles, theta and phi. And these red surfaces are constant r surfaces. And then these green surfaces are constant t surfaces, and lines like this are constant v surfaces, and lines like null lines like that are constant u surfaces. So in other words, this is a u, a retarded time direction, and this is a v, where v is t plus r. Okay, so hopefully the structure of this is clear. So now if we want to, so usually in a scattering process where we scatter massless particles, we want to compute overlaps between states that are defined at scri minus and states that are defined at scri plus. If you also have massive particles, you also have to be careful about I plus and I minus, which is where massive particles come from and go to. So now it's a fact that, and I should say that the natural Cauchy slices in this case are these green surfaces. And in particular, you can also take a limit where this green surface basically approaches scri plus and scri minus respectively. So in Minkowski space, both past null infinity and future null infinity are also Cauchy slices. And so I can choose those to be the slices I evaluate my charges on. And you can take sigma, for example, to be scri plus. And then the boundaries of scri plus, for example, would be sort of two spheres in the far past and far future of this null cone. So we call this scri plus minus. And scri plus plus. and both are two spheres. So the natural, but if you look at one of these Cauchy slices, the natural places where you would be evaluating your charges would be sort of here, right? This would be the boundary, the common boundary of collections of these Cauchy slices, of these green Cauchy slices. So if I want to look at my large gauge charges, I would be wanting to like evaluate them essentially at I0, but you can instead also evaluate them at scri plus minus and at scri minus plus. So Q sigma are defined the common boundary of the Cauchy slices sigma here, these green slices. So in other words, they are defined at scri plus minus and scri minus plus. You can also define them at I0, but you have to be a bit careful. Anyway, so let's think of them as basically living on these past spheres of scri plus and future sphere of scri minus. And so one can check that Q plus, so I'm now going to define Q zeta plus as Q zeta evaluated at scri plus minus. Sorry, am I indicating this here? So I should say that this bit here is scri plus minus, and this sphere here is scri minus plus. So
those aren't just I0. You technically look at the boundary is I0.
no, because I0 is really a cylinder when you blow it up, and you can think about scri plus minus and scri minus plus is the future of that cylinder and the past of that cylinder. And basically what you want to do, there has to be some continuity condition on those charges, and this is what I'm going to be writing down now. So yeah, so if I define this plus charge as Q zeta at scri plus minus, and the minus charge is Q zeta defined at scri minus plus, then one can show so direct computation of these objects in the simple case where we just have charged particles moving along constant, so moving at constant velocities, like we considered in the first lecture. One finds that Q zeta plus and Q zeta minus are antipodally well, I shouldn't say, I should say that the field, yeah, I should say it like this. So the electric field FRU at scri plus minus and FRV at scri minus plus are antipodally related. So why do we care about FRU and FRV? Well, because those are exactly the fields that define our charges, Q zeta plus and Q zeta minus. So in particular, these are precisely the field components that enter our definitions of Q zeta plus minus. So in particular, so we said that Q plus zeta was integral over scribe plus minus of zeta star f. But what is star f in components? So this is a sphere, so I want to look at the dz at the zz bar component of this star f. So this is epsilon zz bar ru fru. Yeah, by definition, this is when I evaluate it on the sphere, this is going to be the relevant component. And then now I can use the fact that the Minkowski metric in these, say, retarded coordinates, so u, r, z, and z bar, takes the following form. So it's minus du squared minus 2 du dr plus r squared gamma zz bar dz bar, where this is just the metric on the unit sphere. After stereographic projection, so I'm just doing this. Yeah, my z and z bar are just coordinates on some complex plane that are related to the points on the sphere, angles on the sphere via the usual stereographic projection. And so we can use this metric to now lower these indices here. So first of all, I can permute this, so the r going past the z and z bar, and the u going past the z and z bar, and then you have to flip the two to get epsilon u r z and z bar. So this gives me a -1, and then the FRU turns out to be yeah, and then you can do a calculation. I'm not sure, did I get it right? So I move it past 2, so you get r z bar, and then the u, you move it past those 3. Yeah, I think there is a minus sign. Yeah, in my notes, I think I have a typo, but okay. So yeah, so basically this, I think, is going to give us, so it's going to be like, well, it's also FUR, and this is GUU FUR GRR plus GUR GRU FRU. What?
So like initially with star f, you're summing over the RU.
Yeah.
So should the RU below be better than R?
I'm not sure. I mean, I thought that star f mu nu is epsilon mu nu rho sigma f rho sigma.
Okay.
That's what I'm using. So, okay, up to a sign, basically what we see. So G upper UU and G upper RR. So G UU upper you can compute from that metric, it's a 0. So this term goes to 0. So and the GUR, GRU are just 1 together. So you just get FRU. There is potentially a sign, but okay. And so this means that I can plug this in here, and we get that this is equal to minus integral over sigma x FUR. Yeah, evaluated on the sphere at scri plus minus. So when you actually look at this field, for example, in the simple cases, it's essentially like FUR that you have to look at and see what the continuity conditions are on FUR as you move from scri plus minus and scri minus plus. And the claim is that, okay, the Q minus is defined similarly in terms of FVR, where V is now an advanced time. And when you look at FUR and FVR, at the linear Vector fields that we computed in the first lecture, you find that in the limit where you approach FUR from above, when you approach the sphere from above, and when you approach the sphere at scri minus, at the future boundary of scri minus from below, those two fields are going to be related up to an antipodal map. And that gives us suggests a condition on these charges. So those charges are going to be related up to an antipodal identification of both the fields and the gauge parameters at scri plus and scri minus. So we obtain a matching condition for Q plus minus, namely that Q plus zeta sorry, this I'm already defining, this there's no point, is Q minus zeta and I'm going to leave the antipodal map implicit in the definitions of these charges, okay? That is to be understood that whenever we evaluate things at scri minus or on cuts of scri minus versus whenever we evaluate things on cuts on scri plus, the coordinate systems on those two cuts are going to be related by an antipodal transformation. So this matching condition, you can also think about this matching condition as just saying that there is no, the charge is conserved as you evolve in time. So so again, I'm going to draw this picture. But in space-time, this is just like, you have a collection of Cauchy slices. So this condition basically corresponds to the fact that the charges conserved in time. Because it really, as we touched upon before, this I0 here, it looks like it's just a point or a two sphere on this diagram, but you should really think about it as, should blow it up and think about it as a cylinder. And so it's just saying that, so this is like a cylinder. And so the charges evaluated at the past cut of that cylinder is equal to the charge evaluated at the future cut of that cylinder, or equivalently from a space-time point of view, the charges are conserved in time. But this is the usual notion of charge conservation that we have in, like in quantum field theory. And so if you think about the S matrix as sort of like the exponential of some Hamiltonian and generating some roughly speaking, if you think about the S matrix as generator of time evolution, then conservation of charges in time should imply that the charges commute with the S matrix, right? Okay, and it makes sense to write this formula here because my Q plus and Q minuses are, these charges are actually identified via the relation that we just talked about before. Yeah, so this conservation of charge, or this matching condition that implies a conservation of charges in time, implies basically a Ward identity on the S matrix via this formula, which I can now choose to evaluate in different bases of asymptotic states, which is what we are going to do next. Okay, so this may have created a bit of confusion, but it should, like this matching condition, because I haven't actually written down the fields and motivated it properly. However, I just want to say that you can just take this condition as given, and namely the fact that we have some relation between the charges evaluated at the past boundary of scri plus and the future boundary of scri minus. And then hopefully it's clear from this picture that this condition, this relation between these two charges, amounts to saying that the charges are conserved in time, and hence it's reasonable to impose that they commute with the S matrix, right? So you can now just assume, if you didn't follow the discussion about matching condition, we're going to talk a bit about it maybe also later in gravity, but you can just assume this relation and see what its implications are. Because we know we have defined these objects, Q plus zeta and Q minus zeta, and so we should be able to actually like see what this condition implies for scattering amplitudes. So let's call this, I don't know, like, so we can assume this and study its implications on scattering amplitudes. So basically, I want to take this relation and sandwich it between some in and out states with certain properties. So we're first going to like do it for in and out states that are usual Fock states, and then we're going to do it for in and out states that are eigenstates of these charges. So we're going to look at both those cases. But before we do that, we need one more ingredient, namely like a more sort of a bit more of an explicit formula for these charges. So how do we go? So far I have written down some like classical sort of formulas for these charges. So how do we figure out how these act on our Fock space or like state space, asymptotic state space, right? In this context, you want to figure that out first. So let's see how to do that. So we look for formulas for Q plus minus in terms of creation and annihilation operators, basically. Right, this is what we want to have. And then once we have those, we'll be able to like see what the implications are of this relation. So to see that, let's take our formula for this Q zeta. So, and let's in particular look at there's going to be, I'm not going to run through both of the, I'm not going to compute both Q plus and Q minus because the computations are basically identical up to this antipodal whatever matching condition, and this basically changes of coordinates between retarded and advanced. So let's just do it for the retarded ones. So we have integral over the boundary of sigma of zeta x star f. This is the formula we derived last lecture. And we can write this as, using the Maxwell constraints, we can write this as integral over sigma of d zeta wedge star f plus zeta x star j. This is what we had before. Assuming that well, this is actually all there is. If sigma is just the Cauchy slice in Minkowski space, not scri plus or scri minus, you just get sigma. If you take sigma to be scri plus and scri minus, you also have to worry about what happens, like what happens there. And we're always going to assume that q zeta here vanishes. But okay, but before doing that, yeah. So this is sort of the formula, and now take zeta to be sigma to be scri plus. So in this case, we can just evaluate these two terms. So the important one, the more important one, is going to be this one. Sorry, so I hope this is clear, all right? I'm just using Stokes' theorem to write this as integral over sigma d zeta star f, and then the first terms comes from acting with the d on the first factor here, and the second term comes from acting with the d on star f under the assumption that d star f is equal to star j. We are allowing for matter particles. This is what we have. So in this case, we have this term basically becomes okay, with a minus sign, dz zeta fu z bar minus dz bar zeta fu z. So I'm working in these retarded coordinates that we introduced before. So yeah, to see this, you have to compute the pullback of this 3 form on scri plus, and just from this picture. So this is an exercise. Actually, let me leave it as an exercise. I mean, compute the pullback of d zeta star f on scri plus. It essentially amounts to that. But why does this make sense? So let me just show it from this picture. So here, roughly speaking, we have scri is like a null cone that's parametrized by u, and then each cut at constant u is a two-sphere with volume form dz bar. So roughly speaking, we want to be looking at the u z bar components of this 3 form, right, when we compute the pullback to scri. And you'll find that this is what you are going to get under the assumption that du zeta is equal to 0. So we're going to assume that this gauge parameter is independent on time. Yeah, do people, roughly speaking, see how that formula comes about? Yeah, anyway, you have to be a bit careful to do this calculation, because naively you may also imagine that you have some potentially RZZ bar components, but those turn out to be subleading. So yeah. So now now putting in also the measure, I mean, more explicitly, we can write this as integral over du d squared z gamma z bar r squared dz zeta FUZ bar plus DZ bar zeta FUZ. Yeah, the volume, it's like the star of the volume form at Scry is just this. Oh, sorry, sorry. This just comes from the volume form. Yeah. And anyway, so you can check this formula. So now I want to. So this zeta is actually U independent. So the only thing that may have U dependence are the FUZ and the FUZ bars, right? So I can write this as minus d squared d squared z gamma z bar r squared, and then du sorry, you write it this way, so dz zeta, and then du fuz bar minus the same thing yeah, and we want to study what this thing is. And naively, you can see that this is a zero mode by noticing that this is just the zero frequency component of the Fourier transform of the field strength. Right? We have such formulas. So this means that this is a zero mode of FU Z bar, and similarly for the other factor. So in particular, these contributions to the charges upon quantization will become zero frequency photons. So let's see how that works. So first of all, FUZ and FUZ bar are the radiative components of F mu nu, and upon quantization, their Fourier modes will correspond to positive and negative helicity photons, respectively. So let's see how this works. So what we have to do is to just expand the gauge fields in modes like you would do in quantum field theory. When you have a classical field, you can write it as a Fourier transform in terms of its Fourier transform, and then you promote the coefficients in the Fourier transform to operators. So we consider have the gauge field at some point x, and then we have sum over positive and negative helicities, integral d 3 cubed over 2 pi cubed 1 over 2 omega, And then also under the integral sign, we have epsilon, the polarization tensors that we introduced before. Yes? So this is just the usual expansion. And now, remember that we want to look at these components of the gauge field in these retarded coordinates u, r, z, and z bar, and we have the following coordinate transformations. So x0, this is t, and then we have x1, x2, and x3. So up to a factor of r, this is just the normal. These guys, you can just compute, they are the normal to the sphere, unit normal to the sphere at some point, the z bar. And AU will be dx mu by du, a mu, and AZ is going to be dx mu by dz, a mu. And what you observe now from these formulas is that the only guy that has the u in it is is a0. So this is going to be like a0, and this is going to be, because of the factors of r here, this is going to go like r times some stuff. Okay? And what this means is that, so assuming, we're going to see in a moment that actually the 1 to 3 components of A are going to fall off as 1 over r. This is the usual fall off of the radiative mode. And hence AZ is going to be order 1 in the large R limit, whereas AU is going to be order 1 over r. But we can already see from this coordinate transformation that there is, I mean, these two differ by a factor of r. Okay? So this is dominating at r as r goes to infinity. So now we want, so I just want now to find a formula. So this is valid at any point in Minkowski space, but I really want to evaluate the gauge field at Scri plus, right? So I want to take the limit when x lives on the future null boundary of this conformal compactification of Minkowski space. So so to do that, first of all, we notice that q dot x, right? This is the only other thing that we need to calculate here. So q dot x is just, sorry, and it's going to turn out to be convenient to introduce, let me write this here. Q is a 4 vector, and it's a null vector, so we have q squared is equal to 0, because this is an on-shell massless field. And then q then can be written as some energy omega times some q hat, that's just going to depend on z and z bar. And this is manifestly, it's going to be something like this, 1. And then there's going to be some q3 vector that's going to be like the unit normal to the sphere at a z and z bar. So using this information, q dot x is omega q hat dot x And since q hat 0 is just 1, and x0 is t, this is minus omega t, and then we have plus omega, and then we have q3 vector now dot x3 vector. But these are both, this is a unit vector, whereas this scales as r, so this can be written as r cos theta, where theta is just the angle between these 3 vectors. So I can write this as minus omega u. So I'm just adding and subtracting an r here. And then we have minus r, and then 1 minus cos theta. Okay, so now and this integral over q now becomes an integral over theta. There is an over theta phi and omega, basically. You can show that. And the idea is that in the limit, so we really are interested in the limit of this formula as r goes to infinity. And we see now that these exponentials here are going to have a piece in them that's going to scale with r. So in that limit, the integrals are going to be dominated by when the coefficient of this r goes to of this r that's now infinite is equal to 0. So first of all, theta 0, this means that q3 vector is proportional to x3 vector. Yeah, so the integral basically localizes to a direction in space-time that points along the direction of the particle. And what we find, so using the stationary phase approximation, one finds that a mu, so as r goes to infinity, the limit of a mu as r goes to infinity is minus IE divided by 8 pi squared r. The factor of 1 over r comes basically from evaluating the integral over the over theta around this stationary phase point. And then we have the sum over helicities as before. And then we have integral from 0 to infinity d omega. And then epsilon mu star alpha. Hat a alpha omega x hat e to the minus I omega u minus the Hermitian conjugate plus order 1 over r squared. Yeah? So these would have been integrated over, but because of this condition in the stationary phase approximation, the spatial Q's that are being integrated over are basically localized around the point in space-time here, x, so around the same point at scribe plus. And then we are just left with an integral over the energies in this formula, right?
Sorry for this. The expression is Q equals to X.
Yes, exactly. So yeah, so basically like stationary phase approximation tells you that you take the exponentials, you expand around theta equal to 0. So this becomes a Gaussian integral. So it's going to be like an integral over basically d theta e to the r theta squared times theta, because there is a sign in the measure. And then you can just evaluate that via change of variables to give you a factor of 1 over r and also a factor of 1 over omega. But that will cancel with corresponding factors of omega in the measure. And then everything else gets evaluated at the stationary phase value of Q 3 vector. Yeah. So this, I should say that this is also done in detail in these lectures by Strominger. So so using this, one can now, okay, and there are some explicit formulas for these polarization tensors, and one finds that basically epsilon mu is like plus is like dz of q times 1 plus, sorry, q hat 1 plus zz bar, and epsilon minus is dz bar q hat 1 plus zz bar. And you can check that basically these formulas ensure that the polarization tensors are orthogonal to the direction of the momentum q. And using these formulas, plugging them in here and performing these coordinate transformations, we find that AZ, which is what we are looking for as a function of UZ and Z bar, so basically evaluated at Scri plus, is equal to E minus I square root of 2 divided by 8 pi squared 1 plus ZZ bar, and then integral from 0 to infinity d omega, and then a plus of omega x hat e to the minus I omega u minus a minus dagger times e to the plus I omega u. Yeah, and then this x hat just is depends only on the z and z bar according to some formulas that I've written down before. Oh, sorry, x hat. Sorry, x is r x hat. That's the notation I'm using. Okay, so this formula is very useful because now we are looking for, remember, we are looking for FUZ, right? We wanted to show, or really we wanted to understand what this FUZ component of the large gauge charges, how that depends on the creation and annihilation operators. Well, on FUZ and FUZ bar, but these ones are, so, sorry, AZ bar is just going to be AZ dagger, and AU is going to be order 1 over R. So AU is suppressed by 1 power of r with respect to AZ and AZ bar, which means that when I write down FUZ, for example, the only thing that the leading term here is going to be DUAZ. Right? Because DZAU is going to be suppressed by 1 power of r, and we're going to be interested in evaluating this at large r. And so, are there questions so far? Okay, so now integral from minus infinity to infinity of du fuz, we can just compute it. And it is yeah, so it's just, let me call, I don't want to carry around this factor. I mean, it's kind of useless. I'm just going to do it up to that coefficient. So it's integral from minus infinity to infinity du, integral from 0 to infinity d omega, and then we have du of this expression, which brings down a factor of minus I omega in the first term and the plus I omega in the second term. So you have minus I omega over all, and then we have a plus omega x hat e to the minus I omega u plus a minus dagger omega of omega x hat e to the plus I omega u. And I should really have said already before that you see that the fact that we have a z-index here matches with the fact that, so we're doing this expansion in near scribe plus. So these guys should be creating positive helicity photons in the out state, which indeed is indicated by the fact that we have an A plus that acting on the, which acts on outgoing states by creation of a positive helicity soft photon. And similarly, we see this here. And now, explicitly, we can just evaluate the integral over u. And this will confirm, of course, that this is a 0. Actually, the integral over u is going to pick up the 0 frequency component of these integrals, right? Because the only thing that depends on u are going to be these exponential factors here. So we have these integrals are going to give deltas of omega. And then the integral from 0 to infinity over omega is just going to pick out the limit when omega goes to 0 of minus I omega, and then a linear combination of these creation and annihilation operators. So this is going to be equal to the omega A plus delta omega plus A minus dagger delta omega, and then there is a 2 pi from the integral, and then this is minus 2 pi I, and then there is a factor of a half because we don't have integral. We have only integral over omega from 0 to infinity, so we work in a convention where the integral of that over delta of omega is basically gives a half times the coefficients evaluated at omega equal to 0. So this times the limit when omega goes to 0 of omega A plus plus A minus. Okay? So this is manifestly 0 frequency linear combination of modes. So this is one component of the charges, and then the other component of the charges, it's just a similar calculation. The currents are going to be quadratic in the fields, so those formulas are going to be quadratic in the modes, and they're basically going to generate some gauge transformation on the asymptotic state. So first of all, so with this knowledge, we can consider the first case. So we take, so evaluate Q S minus S Q in a basis of Fock states. So basically, like, and then A matter something like this, acting on some vacuum. So take this to be in, and similarly for out. So yeah, we just have like some in state that consists of finite energy photons and finite energy like charged particles. And then similarly an out state consisting of finite energy photons and finite energy charged particles. And so we get out. I'm going to abbreviate this by Q zeta commutator with the S matrix. So Q zeta commutator with the S matrix is equal to 0. And now remember that, so what we have learned is that this Q zeta has a contribution in it that is basically proportional to the integral over d squared z. And then we have dz zeta fu z bar plus complex conjugate plus Hermitian conjugate, sorry, integral over, and then integral over du of that. But this we have just computed, and it's just proportional to the limit as omega goes to 0 of omega, and then it would be A minus omega z bar plus A plus dagger. So this is one component, and then there was also the other component that was integral over zeta star j. Right, and so I'm going to define the first bit. So this, the key thing about this term, as I said in words, is that j is quadratic in the field, and hence it's also going to be quadratic in the modes. Whereas the first term is linear in the modes, okay? So I'm going to call the linear piece, I'm going to denote it by QS, which comes from soft charge. And then the other bit, I'm going to call it Q hard, so hard charge. So this linear in modes, quadratic in modes, this is how you can distinguish the two, or like how we define the two. And now this equation here, you see that this tells us is equivalent to, I can, using the splitting, I can write this as out Q soft zeta S in is minus out Q hard commutator with S. Yes? But on the left-hand side, for a judicious choice of a zeta, and using, okay, there is one tricky thing that I haven't said, namely that you can check that these two terms actually turn out to be equal to one another up to some integration by parts, and then choosing a zeta to be a particular function that turns this into a delta function localized at a particular point on the sphere. On the left-hand side here, we're gonna, this commutator is gonna amount to inserting a soft photon in the out state, or equivalently in the in state. So choose zeta to be 1 over z minus w, such that the zeta bar of this is delta function of z minus w. Then we find that this key equation, the conservation law here, becomes basically something up to some coefficient. We find a plus my omega x hat in. So this is from the left-hand side here, right, using this expression. Sorry, and the limit as omega goes to 0 of omega times this is equal to minus out q zeta hard. Sorry, I'm h. I have this as h as in. And now you can actually check using this quadratic formula. I'm not going to go through this. Like you can do an analysis. You can write down, for example, you can take like scalar QED like we did before, and write down the current associated to the scalars. It's going to be quadratic, basically given by the usual formula, quadratic in psi and psi bars, where psi are the scalar fields, and then you can do the mode expansions of those, and you're going to get a formula, quadratic in the modes, and then you can act with that on the out states and on the in states, and basically both the in and the out states taken to be Fock states will basically diagonalize this hard charge with a certain eigenvalue. And you can actually show that the right-hand side is equal to, can be recast or like massaged into sum from I equal to 1 to n, where n are all the external particles, qi epsilon plus dot pi divided by pi dot q. And the way to see this is to notice also that, of course, for the same choice of zeta that I'm taking here. And the key thing is to notice that actually this factor is equal to sum, so up to a coefficient, sum from I1 to n, qi divided by zi minus w. So it's just by direct computation of this factor using the formulas for, sorry, assuming but it actually also works for massive guys. It's just that this formula is going to look a little bit different. But this equation is still going to hold. And the result is basically now that the conservation law, so this assumed conservation law for these large gauge charges, implies ward identity for the S matrix the same when you evaluate it in a basis of Fock eigenstates as the soft photon theorem. So this is what we discussed. We discussed this leading soft photon theorem in the first lecture. Questions about this? Yes, sorry, I should have said. These QIs are the charges of the external particles. So yeah, so here we have the exact same picture where we have like a process where we have the emission of a photon, and then we have like charged particles of momenta pi and charge qi. And in the limit when q goes to 0, this becomes this soft factor S0 times the amplitude without the soft photon. And the point is that this equation can be obtained from the conservation law for the large gauge charges. Or it is the equivalent to the conservation law for the large gauge charges. So yeah, other questions? The second option is to take the basis to be eigenstates of this of these q zeros, and so now we have so let me write it like this: q out, q zero as q in is equal to 0. Yeah, so these are different from, so notice that while our usual Fock states do diagonalize the hard charges, the Fock states don't necessarily diagonalize the soft charges, because the soft charges actually insert a soft photon in the vacuum. But you can switch to a basis in which they do. And in this case, what we learn from this is that the this conservation law now implies that Q in is equal to Q out. Or equivalently, Q in soft plus Q in hard minus Q out soft minus Q out hard is equal to 0. But the difference between Q in hard and Q out hard is still going to be given by this soft factor here. It's going to be so I'm assuming that whatever I do to the asymptotic states to diagonalize these charges must only affect the soft charges, because my hard charges, like my usual Fock states in the hard sector, already diagonalize the hard charge. I need to just engineer asymptotic states that now also diagonalize the soft charge. So I need to basically, what you're going to see that we can do is to act with some operator on the soft sector of these of the Fock states to also diagonalize the soft components of these charges. But the hard piece remains the same. So this equation now tells me that whatever the difference is between this in soft and in out, it has to match with this with the difference between the charges for the hard charges of the states. So this means that the delta Q soft, define this Q in soft minus Q out soft is minus delta Q hard. So in other words, what we get is an eigenvalue equation for some soft charge eigenstates. So we find that Q soft U out limit when omega goes to 0 of omega times A plus omega plus A minus omega dagger, right? So this was proportional to my Q soft. I want to find U such that U out acting on a 0 soft charge sector, on a 0 soft charge state, is equal to Q out soft. And similarly from the for the in state. Okay, so this will basically like ensure that this equation is satisfied, provided that I choose this soft eigenvalue to be balanced by basically the difference of the soft eigenvalues to be balanced by this guy, by the difference of hard eigenvalues. But basically what this gives me is, so since QS annihilates, I'm choosing the state to diagonalize QS with a 0 eigenvalue, I can rewrite this as a commutation relation for U out. So U out commutator with QS has to be equal to U out times Q out soft. And this is actually like, the solution to this is actually easy to write down once you know that actually we'll see next time that when you analyze the phase space of the theory, these charges Q soft are actually going to be canonically paired with some objects that are going to be also constructed from gauge fields. But for now, let's assume that those exist. So assuming that Q, sorry, I'm going to call this Q soft as a function of Z and Z bar. So without this integration against some arbitrary function on the sphere. So Q soft Z and Z bar, commutator with some other operator that I'm going to call C hat, Z prime, Z bar prime, is proportional to delta squared Z minus Z prime. So we'll see next time. Then a solution to this equation is going to be given by U out is e to some integral over d squared z gamma z z bar Q out soft times C. And this is very similar to how you think about coherent states, for example, in classical mechanics. Usually these are defined as to diagonalize the lowering operator, and then you find that the coherent states are basically given by the exponentials of the conjugate to that lowering operator, which is the raising operator. But here, the charge is linear combination of those, but it still has a canonical pair, and you can actually check that the commutator of Q, provided that you have a canonical commutation relation between this QS and this C hat, that the commutator of Q with this exponential of C hat dressed by a corresponding eigenvalue Q out will basically obey the required equation. And the upshot here is that this is the same is the Fadeev-Coolidge states or dressed states that we discussed before. There is a calculation that one has to do, but yeah, so this is the result. And so doing the same for the in state, you just recover. So the conservation law, now evaluated in a basis of charge eigenstates, turns out to imply this Fadeev-Coolidge dressed state prescription. So the upshot is that the dressed state prescription from last time follows from looking at the conservation law for these Q zetas in basis of Q zeta eigenstate. So, and this, as was checked a long time ago, also like turned out to remove some of these infrared issues at the level of the scattering amplitudes. And so the idea is that perhaps what this shows is that conservation of these large gauge charges, and in particular working with like computing scattering amplitudes in basis of states that diagonalize these charges, at the path integral level should amount to using boundary conditions that impose that these large gauge charges are fixed. And perhaps if one revisits sort of like the way in which one computes scattering amplitudes in QED, for example, using these new boundary conditions and taking into account these, the fact that we have these large gauge symmetries in the problem might naturally allow you to construct infrared finite observables in that case. So, but on the other hand, if you look at the conservation laws in the usual Fock basis, you just recover the usual soft photon theorems that you would get in a quantum field theory with the usual like boundary conditions. Where, yeah. So I guess I don't know what time is it. Let me just check. Oh, sorry. Okay, so then we are, yeah. So then this is basically all I had to say. And next time we're going to look at gravity, and we're going to see like a lot of these ideas generalized in that case. But we're also going to look at the, basically we're going to discuss the covariant phase space and how to construct gravitational charges. In that case, we are not going to have transformation isomorphisms. Those are going to be associated to charges. There's going to be an infinity of them, and we're going to see that the conservation of those charges will imply the corresponding soft graviton theorem. So, yeah, thank you.